Let's jump right into this explainer. We're looking at the fascinating evolution of the tools that help us measure and build our physical world. But from an executive perspective, precision isn't just about getting the math right. It's fundamentally about project efficiency. It's about optimizing capital deployment and guaranteeing a solid return on investment for major infrastructural assets. So today, we're mapping out exactly how technological leaps in surveying have continuously slashed operational risks over time. Have you ever actually stopped to wonder how massive infrastructure projects, I'm talking things stretching for miles, stay perfectly straight and perfectly level without a single error? Think about high-speed rail lines, cross-country pipelines, or massive commercial developments. A miscalculation of just a fraction of a degree, well, that can literally lead to millions of dollars in structural rework, delayed timelines, and massive budget overruns. The secret to mitigating that immense operational risk, it all lies in the tools we use to understand the ground beneath us. And that brings us to surveying. It's an exact science dedicated to the pursuit of absolute physical precision. Put into simple business language, surveying is really the ultimate form of spatial risk management. By accurately capturing the three-dimensional space of a site, we create a rock-solid data foundation. Because, let's face it, without this precise groundwork, any architectural plan is basically just a very costly guessing game. Okay, let's quickly review our agenda for today's roadmap. We'll cover the evolution of measurement, moving from chains to tapes for distance, and compasses to theodolites for angles. Then we'll tackle eliminating measurement errors, the electronic revolution, and wrap up with specialized surveying tools.
Section 1. The evolution of measurement.
Section 2. Distance, chains to tapes. Notice this massive transition here. We went from these clunky metallic chains with brass rings every meter, straight to sleek, specialized woven tapes. Out in the field, a chain that stretches or bends because of temperature changes introduces systemic error, and systemic error translates directly to project risk. So upgrading to steel and Invar tapes was absolutely crucial. It significantly boosted measurement speed and drastically reduced those material deformities, a real game changer for project efficiency. You'll also see that chains definitely weren't one size fits all. They were highly standardized. Take the 33-foot revenue chain, for example. It was optimized specifically for cadastral surveys, basically mapping land boundaries for taxation and real estate. So even back then, you can see professionals tailoring their physical assets to maximize workflow efficiency for very specific business use cases.
Section 3. Angles, compasses, and theodolites.
Right here, we have the two primary tools used for this. You've got the prismatic compass for reading whole circle bearings, and the surveyor's compass for quadrantal bearings. And choosing between these two wasn't just random. It was all about balancing speed versus accuracy. The prismatic allowed a surveyor to sight an object and read the bearing at the exact same time, which, as you can imagine, drastically cuts down time spent out in the field. But notice how the surveyor's compass actually offers a more precise least count of 15 minutes compared to the prismatic's 30 minutes, even though it requires separate sighting and reading steps. By the way, least count is basically just the instrument's margin of error. So if you're managing a project, you've got a critical choice. Do we need the rapid deployment of the prismatic or the higher precision of the surveyor's compass to guarantee structural integrity? Building right upon the compass, a theodolite became the absolute ultimate instrument for finding incredibly precise horizontal and vertical angles. This was a massive technological leap. It's a highly complex optical instrument that drastically reduced angular uncertainty. This is literally what allowed skyscrapers to go higher and bridges to span wider without losing alignment. To really understand the theodolite, we need to define the trunnion axis. This acts as the crucial mechanical pivot point for all vertical telescope movements. For your operators on the ground, understanding terms like the trunnion axis is a fundamental training requirement, because if this axis isn't perfectly perpendicular to the vertical axis, every single reading is compromised. It's that critical.
Section 4. Eliminating measurement errors.
Every single time a surveyor sets up a theodolite, they have to rigidly follow 3 temporary adjustment steps to ensure operational accuracy before taking a single reading. Think of this as your non-negotiable, standard operating procedure, your SOP. Proper centering, leveling, and eliminating visual parallax are absolute musts. Skipping these procedural mandates is honestly the fastest way to introduce compounding errors that will cost your firm heavily down the line. So the crucial takeaway here is that systemic errors, like a non-perpendicular horizontal axis, are actively canceled out by mathematical techniques.
things like taking both face left and face right observations. This is just a brilliant operational failsafe. By taking measurements from opposite instrument configurations and averaging them out, surveyors mathematically engineer human and mechanical flaws right out of the equation. It is pure, process-driven risk reduction. Section 5, the electronic revolution. Electronic distance measuring instruments, or EDMI, replaced physical tapes entirely. They calculate distance using the speed and reflection of different invisible waves. And let me tell you, integrating these digital tools is a massive step forward for any firm's growth roadmap. By sending a wave to a reflector and timing its return, computations that used to take teams of people hours can now be done by a single operator in fractions of a second. The ROI on that speed is incredible. Here we see the Tellurometer, which impressively uses microwaves to survey rough terrain over a 100-kilometer range. Right next to it is the Distomat, a compact infrared device that's absolutely perfect for shorter construction distances. This really highlights the importance of matching your tech to the specific project scale. You deploy the Tellurometer for sweeping regional surveys where physically crossing the terrain is impossible, while the Distomat gives you incredibly fast, high ROI measurements right there on an active commercial job site. Now, for peak accuracy at night, instruments like the Geodemer use modulated light waves. This pushes precision up to an astonishing 25 kilometers in the dark using mercury lamps. In a business context, this is completely revolutionary. It means surveying operations can safely and accurately shift to a 24-hour cycle. When you eliminate daylight bottlenecks, you aggressively accelerate your project delivery timelines.
Section 6, specialized surveying tools.
Beyond the heavy hitters, surveyors also rely on highly specialized tools. Whether it's an auto level for incredibly fast elevation finding or a wheeled perambulator for quick ground distance, there's an exact, purpose-built tool designed to increase efficiency for every physical challenge out there. The auto level essentially calibrates its own line of sight, which strips out manual adjustments and drives up survey speed on massive rotor grading projects. It's all about maximizing your output while minimizing required user inputs.
Which leaves us with a really fascinating thought. If we've gone from dragging chains through the mud to bouncing lasers across valleys, what invisible waves will surveyors harness next to build our future? The long-term scalability of digital surveying is tied directly to emerging tech like drone LiDAR and AI-assisted data processing. As executives and operators, staying ahead of this technological curve is the only way to ensure your future projects are built faster, safer, and with zero margin for error. Thanks for joining me on this explainer, and I hope it provided a clear roadmap of the tools shaping our physical reality.